Welcome, I'm Professor Sever. Today we're going to discuss limits from the standpoint of review in Calculus 1. To facilitate this discussion, I've prepared several problems that we will discuss. So let's look at this first example of basic limits. And you see I have 7 parts here already prepared. Most of these limit calculations are done via functional evaluation. And we have various theorems that tell us why we're able to do that. So for A and B, these are polynomials. We know we evaluate a polynomial just by functional evaluation. Another way to say that using the language of limits is that polynomials are continuous everywhere. So for number A, we just plug in 3 to the polynomial x squared plus 5x minus 8. And I have that result there. The answer to the limit is 16. For part B, we evaluate the polynomial 24t cubed minus 8t squared plus 12 at the value of 1/2. Another way to say that is we just plug in the value of 1/2. We plug into that polynomial and we have the work presented, and the result is 13. Now for number C, certainly that's not a polynomial function that you see here, but we do know that sine and cosine are continuous. That means when we evaluate the limit at any value, we can do so simply by functional evaluation. So again, you see I'm just plugging in the value of pi halves to my function, and we know the sine of pi 6 is 1/2. We know the cosine of pi 6 is √3/2. So we multiply and obtain the following answer. Again, we could simplify by getting a common denominator, which would be 2 minus 5 √3/2. Now, number D, we have to be a little bit careful because tangent and cotangent aren't continuous everywhere. However, pi fourths is in the domain of tangent and cotangent, and we have a theorem that says when evaluating the limit of any of the 6 trig functions, if the value at hand, the c value, which is here, is in the domain, you may evaluate the limit by plugging in. And that's what we do here. The tangent of pi fourths is 1. The cotangent of pi fourths is 1, as you can see here in the computation. So this result for the limit is 2. Now let's go back and let's look in black. We have the typeset statements. In red we have my work, and notice on the right hand side we don't have any limit statements. Why? Because I'm evaluating the limit on the left hand side by plugging in. So the reason there's no limit statement here, I'm evaluating the limit. This statement is the answer to the limit, and then of course the number 2 is this statement simplified. E is another polynomial function. Now it's rational, but it's also polynomial since there's no variable in the denominator. And again, we can evaluate this through the mechanism of functional evaluation. So we just plug in, we get the answer of a -11/3. Now, the next part, F, we have the difference of 2 functions, one of which is polynomial, x/2. So we could evaluate this by functional evaluation, namely just plugging in. And we have a theorem that says if the c value is not 0 for the even root, you can evaluate this piece just by plugging in. And that's what we do. We plug in 16 for x in both pieces. So we get 16/2 from the first function of our difference. And then we have -5 times the root of 16, which is what you get when you plug 16 in for the square root of x. This simplifies down to -12. Now, the square root of x, or the square root function. So the limit as t goes to 0 of root t, that limit does not exist. Why? Because the limit concept is a two-sided concept, and the domain of the square root function is 0 to infinity. There's nothing on the left-hand side of 0. That means there are no values on that side, the left of 0. Therefore, the limit could not exist because the limit from the left would not be the limit from the right. Now, abstract basic techniques. So we have 3 functions, f, g, and h, each of which at the value of c, the limit exists. We have the limit as x goes to c of f of x is 6. The limit as x goes to c of h of x is -3. The limit as x goes to c of g is 11. So we want to evaluate each of these various limits, and we know the limit of the difference is the difference of the limits, so we can simply evaluate the the limit of each piece separately. So this should be the limit as x goes to c of f of x minus 3 times the limit as x goes to c of g of x. And that result simplifies to minus 27. Similarly, we see in part B that the limit as x goes to c of 2 times f is 2 times the limit as x goes to c of f of x, so that's 2 times 6. And of course 12 is a constant function, so no matter where c is going, 12 goes to 12. So this limit is 0. The limit of the product is the product of the limits, provided both limits exist, which they do. Therefore, this would be 2 times the limit as x goes to c of f of x times the limit as x goes to c of h of x, which we have here, 2 times 6 times minus 3, which is minus 36. Again, we have a ratio, and as long as h isn't going to negative 4, which it's not, we will be able to evaluate this limit by the limit of the quotient is the quotient of the limits. So you pass the limit to the numerator, you pass the limit to the denominator, and then you evaluate the limit of each function, yielding 6 plus 22 over 1, which is 28. And again, finally, we have another quotient to consider, and as long as, since the limit of these 3 functions exist, as long as the denominator is not going to 0, which it isn't, it's going to 28, we know that this limit of this quotient will exist. Now, if this limit did go to 0, we wouldn't know how to proceed without more information. Obviously, that wasn't the case here. These are just basic techniques, and that would be a slightly more involved problem. Okay, basic limits. So now we're looking at the next level up. So now we're looking at a rational function in part A. Can we evaluate by simply plugging in, namely functional evaluation? The answer is no. Why? You would have 0 in the denominator. However, you have 0 in the numerator. Let's test that. 1 plus 5 is 6, minus 6 is 0. I was plugging in the 1 to the numerator to see what was happening. And since you would have 0 in the numerator and 0 in the denominator, we call that an indeterminate form. You don't actually have 0 in the denominator. What we really mean to say is the numerator is going to 0, the denominator is going to 0, as t, separately they go to 0, as t goes to 1. This is an indeterminate form, which means you have to do more work. So we have a 0 over 0 form, and that means we need to do more work. Here the more work will be along the lines of cancellation, and again, please note you write the limit at each stage until you are evaluating the limit. So functions that agree at all but one point, these functions are equal, so that's why this equals here. Nothing's happening. This is just rewriting the form. Now we cancel. So this function, which is the original function, is equal to t plus 6 except at the value of 1. Therefore, these functions agree at all but one point. That's what justifies this equal sign. And now this is a polynomial. We can evaluate this polynomial by plugging in. So the answer to the original problem is 7. Here, we can cancel. So the limit as x goes to 3 of x minus 3 over itself is equal to the limit as x goes to 3 of 1, and that's where the x minus 3's cancel. That says the function 1 is equal to this function except at the value of 3. Again, that's functions that agree at all but one point. And then we cancel, and then we evaluate the limit as x goes to 3 of 1. That's just 1. Now this one's a little interesting. So if we look at each piece separately, again, we're plugging in to figure out where the limits go because these are rational functions, or where they would go. This left-hand factor goes to 0. 1/2 minus 1/2 is 0. Now, can we evaluate this limit? So if I only look at the denominator, so in my mind I'm looking at the limit as x goes to 1/2 of just 2 minus 4x, that goes to 0. So this left-hand factor would go to 0. This factor is undefined, so we have a 0 times an undefined. That's, again, another indeterminate form. And what that means is we can't say, looking at using that level of analysis, we can't say what 0 times infinity is. That means you have to do more work. So what we do is we get a common denominator and we multiply. So this would be 1 minus 2x over 2. Multiply, factor, cancel, and we see we have a common factor of 1 minus 2x. I'm leaving the algebra to the reader. Remember, this is a review of limits, so I'm leaving the algebra to the reader. I'm just trying to concentrate on the calculus. These would cancel, so this function 7/4 agrees with this function in all but one point, namely 1/2. Therefore, this limit is 7/4, and of course this limit is equal to the original limit because this function and this function are identical. Finally, we have a limit, our first limit in the course, where we do not evaluate it by functional evaluation or by using the theorem functions that agree at all but one point, which is, the way we think about it algebraically is a cancellation theorem. So first off, we move the 2 outside. So there's really 1/2. We're moving out 1/2. Constants can come out of the limit. That's what happens on this first step. And now we look at this limit. We know this limit is 1, right here. We're evaluating this limit. This is well known. This is a theorem. The limit is, as x goes to 0 of sine x over x is 1. Therefore, the theta is a dummy variable. It doesn't matter what it is, provided these three things here, here, and here are all theta. This limit will be 1. And so now 1/2 times 1 is 1/2. And that's really how you would show the work. Also, what I'm doing is I'm not just providing the answers. I'm also modeling how the work would go. So the work here is you show the cancellation. The work on this problem C, you show the cancellation. We know that you're using functions that agree at all but one point. Here, you pull out the 1/2, so you get this piece alone, which we know is a theorem. So we don't have a theorem which says, what's the limit as theta goes to 0 of sine theta over 2 theta? So we don't have a theorem for that. Why? Because we don't need one. Because we can move this constant out, and now it's 1/2 times the limit as theta goes to 0 of sine theta over theta. That limit we know is 1, so now we can evaluate the limit of this function at 0. I'm Professor Sever. Thank you for watching a review of limits.